Ore deposits are extremely rare occurrences. Combined natural processes of igneous, sedimentary and metamorphic processes and tectonic activity have carved out ore deposits of widely differing sizes, shapes and kind out of the commonly available starting material, the average crust. We are also aware of the fact that various ore deposits are not equally distributed around the world. Some countries are extremely rich in several or some particular ore deposits, while others are not. This definitely proves that geography and political thinking of a country does not dictate where a mineral deposit is to be found and where should it end. A mineralized belt of a specific metal will not end abruptly simply because of international borders. The belt of copper molybdenum mineralization extends for thousands of kilometers on the western coast of the Americas through several countries. Same could be said for the tin ore occurrences in the countries around the Atlantic Ocean. Thus, on a global basis, one could say that a number of metallic and non-metallic deposits are restricted to some specific localities. This will mean that chances of finding future deposits of metal concerned are more here than elsewhere. In short, we can say that mineral deposits are thought to be confined in space. We shall discuss the theoretical as the same time applied theme under the following heads: metallogenic province, typical examples of metallogenic province of primary origin, typical examples of metallogenic province of volcano sedimentary origin, metallic provinces, Indian examples, and fifth, genesis of metallogenic provinces and their use in mineral prospecting. The two related concepts of metallogenic provinces are metallogenic epochs and metallogenic province. Province tells that formation of ore deposits in space and time are not haphazard processes. Metallogenic province specifies space, while metallogenic epoch time. The former represents a huge area measuring in thousands of square kilometers, where characteristic mineralizing activity has been operative, often in several episodes. It may be just for one particular metallic ore deposits or a number of them. Some of the best examples of metallogenic province includes tin provinces of southern Europe, Southeast Asia and Eastern Australia, Precambrian nickel sulphide deposits belt of Ontario, Manitoba and Ongwa in Canada, and the sandstone hosted uranium deposits of western United States and Canada covering several states. Banded iron ore formations of Precambrians around the world are also what constitute a metallogenic province. Even though of sedimentary origin, whatever the processes involved, the whole region need to be characterized by a particular assemblage of mineral deposits. Also, for the variety of ore deposits, a number of mineralizing episodes, what we call metallogenic epochs, were responsible. Quite a few examples can be cited as examples of metallogenic provinces, but for want of time, only those few will be mentioned which are most typical and recognized by almost all. These include Metallogenic Tin Province. Four well recognized metallogenic province of cassiterite include those of southern Europe, Africa, Southeast Asia and Eastern Australia. In most of these cases, epigenetic tin mineralization is associated with post-tectonic granites and pegmatites of post-Precambrian age. According to Evans, on a worldwide basis, approximately Mesozoic granites are responsible for 63% tin deposits, while 18% to Paleozoic granites, 6% to mid-Paleozoic and 3.3 to Precambrian. The two belts of southern Europe, including Cornish granites of Britain, France, Italy, Spain and Portugal, have been famous for their hydrothermal cassiterite deposits. And then we have porphyry copper molybdenum provinces. These are giants of the ore world, though of lower grade. Main element is copper, but other associated include molybdenum, gold and less commonly tin and tungsten. Their enormous size, specifically those of Chile and Peru of the Andean belts that extend well into western United States, qualify them to be one of the most typical examples of a metallogenic province. Age-wise, they are either Mesozoic or Tertiary orogenic belts and hosted within rocks of the granitic to granodioritic clan rocks like adamelite, granodiorite, tonalite and quartz monzonite. They are, as per the current thinking of new global tectonics, product of oceanic continental subduction, typical example Andean belt, or linked with oceanic plate subduction in the island arcs environment like in Philippines, Solomon Islands and others in the western Pacific. Then we have copper province of southern United States, a huge region in the two states of US, Arizona and New Mexico. Parts of northern Mexico are dotted with several major and small copper mines and easily qualify for a copper province. Then we have gold province of the Canadian Shield. It is one of the outstanding metallogenic province for gold, extending for over 3,200 km and including a number of gold mining camps and districts. Then we have nickel sulphide deposits. These are typically hosted in the Archean greenstone belts and are good examples of metallogenic province. Regions include Manitoba, Ontario and Ungawa, all in Canada, the Western Australian Shield area, Zimbabwe and northern Baltic Shield areas. We have then anorthosite hosted titanium oxide ores, mostly confined to Proterozoic. Ores of FeTi oxide lie within the mobile belts of Gondwana land and Laurasia. Examples in Canada include Saint Urbain and Allard Lake deposits in Quebec, Bergen, Loften and Egersund in Norway, and those of United States of America at the famous Iron Mountain of Wyoming and New York, Sanford Lake. Others. Other deposits include, space will not permit to give other examples, maybe not so large as they are in North America. Some of them include the Witwatersrand and Free State gold provinces of South Africa, Zambian and Katangan copper provinces, Siberian Shield gold province, Platinum province of Urals and Georgian manganese province, and Scandinavian nickel province, German lead province, and the list will not be complete without the mention of Australian gold province of Victoria and New South Wales, and a large lead zinc province at Mount Isa in Northern Territory in Western Queensland. In module 3 we shall see typical examples of metallogenic provinces of volcano-sedimentary origin. Earlier the term metallogenic province was restricted to epithermal hydrothermal deposits. However, currently the concept is also applied to sedimentary, volcano-sedimentary types of deposits, considering their vast expanse. Another point to remember is that the concept of metallogenic province cannot be applied exclusively. It will generally be related to time factor. Thus, within a metallogenic province, there might have been a number of episodes of mineralization, what is referred to as metallogenic epochs. Some of the most typical examples of metallogenic province of secondary origin will include banded iron formations with typical bending of alternate hematite quartz layers. These massive formations are the backbone of world's iron and steel industry. These are more or less exclusively confined to the Precambrian, that is 2500 to 1900 mm ago, transformation to oxygen rich atmosphere during the Proterozoic, mainly early Proterozoic, was the key factor. Surprisingly, BIFs were not repeated again in the geological history. However, later, that is in the Phanerozoic, iron rich sediments with combination of hematite, chamosite and siderite do appear on a fairly large scale, like the minute ores of Midland UK, iron ores of Alberta and Lorraine and Luxembourg, the Salzgitter of Saxony in Germany. These may constitute metallogenic province on a limited scale, and earlier the ores were much favored due to their self fluxing, that is because of the presence of carbonates. The best example of the BIF is of course the world's largest, that is Lake Superior area of Minnesota and Michigan and Wisconsin, up to 600 meter thick and traced for hundreds of kilometers. Same type of BIF also occurs in the eastern states, that is New York, New Jersey and Pennsylvania, and the western states Alberta, California and Texas. Others include those of Hamersley in Western Australia and several areas in Brazil, Lake Superior region and Labrador Trough of Canada, India and USSR and Transvaal of South Africa. Coming to volcano sedimentary metamorphosed manganese deposits of the world, perhaps could also be considered as metallogenic province, though their example is better known for metallogenic epochs. But since there is close genetic relationship between precipitation and deposition of iron and manganese, there need not be any objection. Some of the largest deposits of Russia, Ukraine and Bulgaria come under this category. Nikopol Basin in Ukraine is the greatest deposit of all, containing 60% of world's reserve. The manganese province of central India is yet another good example. Coming to uranium provinces of North America. Sandstone hosted uranium has been mined in the Colorado Plateau since 1896, used to give intense red color to ceramic ware, and the entire region is a good example of uranium province, resulting due to deposition from circulating waters that collected uranium from dispersed sources. New discoveries were then made in New Mexico, Wyoming, Utah, Colorado and Texas, which are called uranium province of western United States, as also in Blind River, Ontario, Canada and South Africa, Witwater Strand, Banket ore. Next example is Mississippi Valley lead zinc ore deposit. This unique deposit has posed several problems for geologists. Firstly, these were blind ores in a region of little relief and surface outcrops, later on proved to consist of numerous but small erratic and irregular ore bodies and were not controlled by any structures. However, they constitute a metallogenic province formed by the expulsion of metallic bearing pore waters from the sediments. Indian geological scene also presents several good examples of metallogenic province, though may not be on a jumbo scale like elsewhere. Some of these include copper uranium province of Singhbhum shear zone. This is perhaps the oldest copper mining region in the country. Mining in Singhbhum district apparently began as early as 2000 BC. The mineralization is linked to a shear zone and the country rock comprises Precambrian chloride, garnet, mica schist and to some extent of Singhbhum granite. The belt, ranging in width up to 5 km, extend for nearly 130 km from Daurapuram to Barahagora in the southeast. The most important copper ore is chalcopyrite, which is associated with pyrite and pyrrhotite. The most important localities include Pathargoda, Rakha, Rom Siddheshwar, Ramchandar Pahad, Tama Pahad and Turumdih. The next in importance is west-northwest, east-southeast trending Hesetu Belbahan belt, 50 into 250 kilometers in extent, from Hesetu in Hazaribagh district to Belabathan in Goda district. Important locations include Baragonda, Chanadio, Jalalkhira, Damgi, Tulistner, Bagmari and Pira. The mineralization is in the form of lenses and pockets within Chota Nagpur granite gneisses associated with amphibolites, tremolite, actinolite schist and calc granulite. Next comes the Khetri copper belt and Purbanera Bhindar belt. Advanced copper mining in this region may have begun in post-independence time, but this too has witnessed mining by the ancients. Mining was definitely in progress here during the times of Mughal Emperor Akbar. Khetri copper belt in Jhunjhunu district of Rajasthan runs for about 80 km and is located in a northeast southwest striking zone dipping 70 degrees to the west and composed primarily of amphibole quartzite and crystalline schist of pre-Aravali and Delhi group of rocks. The mineralization is along favorable structural zones like shear planes, cleavage planes and joints and consists of chalcopyrite, pyrrhotite and pyrite. The important deposits and mining centers centered around Madan Khudan, Kolihan and Chandmari. The Purbanera Bhindar belt is even longer, 135 kilometers actually. There are 4 smaller belts with Purbanera, Jasma, Rewara, Karo, Rajpur Dariba, Bethuni and Wari Bhopal Sagar. Most important deposit is at Dariba. Then comes the hydrothermal gold province of Karnataka, Andhra Pradesh and Tamil Nadu, including Kolar, Hatti, Anantpur, Gadag and Wayanad. This important province comprises mostly dharwars, now metamorphosed to amphibolites from original metavolcanic rocks. Other rocks include muscovite, biotite, schists, quartzites and granulites, as also peninsular granites and gneisses. Dolerite dikes and pegmatites of younger ages represent the final phase. Ores are mostly of hypothermal range and are represented by 3 zones: Gadag, Chitradurga, Mysore zone, Ramgiri East, Bangalore zone and Hatti, Kolar, Mamandur, Vellore, Tirupati zone. Mineralization is hosted in schists confined to quartz vein and sulphide bearing reefs. Next comes manganese belt of Balaghat, Bhandara and Nagpur in central India. This province has the major share in India's manganese ore production, over 40%. Gondites, the home for manganese ores consisting of quartz, spessartite, rhodonite and manganese amphiboles, were formed by high grade metamorphism of manganiferous clastic sediments stretched for over 150 km in what is called manganese belt of the country, that is Nagpur, Bhandara, Balaghat belt. This is undoubtedly the richest manganese region of the country and also perhaps one of the best of the world. Iron ore province of Bastar Durg in Chhattisgarh and Singhbhum, Khenjar, Sundargarh, Mayurbhanj in Jharkhand and Odisha, Maharashtra and Goa. Iron ore is by far the most important mineral resource of our country. Lake Superior type BIF has large exposures in several adjoining states and can conveniently be described as the iron ore province. There are some differences mineralogically with the type area of the world. However, in richness they are second to none and make one of our major mineral exports. Coming then to kimberlites and lamproid province, the source rock for diamonds. It may be debatable whether to include these as metallogenic province, but from practical point of view, the three large regions, that is Panna diamond field belt in Madhya Pradesh, Vajrakarur region in Andhra Pradesh and Raipur Bastar districts of Chhattisgarh more or less qualify as diamond province, both from the primary source, that is kimberlite and lamproid, as also for secondary diamond sources, conglomerates, gravels and stream placers, etc. Then there are some other examples. In post-independent India, Malanjkhand copper region in future has the capability of acquiring a metallogenic status, and the lead zinc deposits of Rajasthan, including the Zawar, Rampur, Agucha, a strata-bound deposit, has already a province of substance. Origin of metallogenic province is not without doubt and questions. Some believe that presence of metallogenic province, that is particular assemblage of mineral deposits of metal or metals, or by a distinct style of mineralization in a particular region, owe their origin due to processes of magma generation, sedimentary basin formation and metamorphism, which themselves are controlled by earth processes that are larger and space the face of the earth. However, others rightly believe that metallogenic provinces are not caused by local and normal petrogenetic processes. If we consider at micro level, metallogenic provinces can only be a specific expression of a geochemical province, which is abnormal geochemically, and the cause is rooted deep within the mantle. It is suggested that abnormality of the mantle composition, which we call mantle inhomogeneity, both vertically and laterally, with respect to one or more elements, is the root cause. This has resulted in producing ore deposits in that restricted area in several episodes and several different rocks. In fact, the bona fide geochemical or metallogenic province should have witnessed same metallogeny in more than one episode. As mentioned above, the whole concept of metallogenic province is not without doubts and uncertainty. For example, there are where the abundance of a particular element of interest in the associated host rock or its differentiates is several times higher than for the average rocks. For example, abundance of tin in late differentiates from the metallogenic tin province of Southwest Asia is several times higher than average igneous rocks. There is yet another study which places tin content of micas from pegmatites of Southwest Asia to 10 to 100 times higher, as much in comparison to mica from similar pegmatites which show no tin mineralization. However, from other tin bearing regions, there is no evidence that granites hosting tin mineralization are significantly richer in tin from other granites not having anything to do with metallogenic province of tin. Ahrens and Liebenberg have said that in spite of relationship not being absolutely clear, one thing is certain. However, from other tin bearing regions, there is no evidence that the granites hosting tin mineralization are significantly richer in tin from those granites not having anything to do with metallogenic province. In spite of the relationship not being absolutely clear, one thing is certain: there are large provinces with metal or metals deposits of certain types of mineralization around the world. The modern concept of plate movements seem to supply a tangible answer to the question. Agreed that there exist metallogenic provinces, but what causes them to be there where they do? Plate movements of convergent and divergent nature both cause great degree of magma generation and metal rich hydrothermal solutions, which will cause ore deposition on the massive scale that define metallogenic provinces. There can be no clearer example than afforded by the great porphyry, copper, molybdenum deposits that extend from Chile and Peru and beyond into North America. Cause Ocean Pacific plate subducting beneath the South American continental plate. Other examples given in earlier modules will confirm the same idea. Other types of boundaries and mega features of the global tectonic concept like passive boundaries, hotspots, mantle plumes, all could be cited capable of generating metallogenic provinces. Space will not permit to give for two examples will be cover the point. Number 1, constructive margins, Cyprus type deposits, alpine type chromite deposits associated with Red Sea. Second, destructive margins, copper, molybdenum, porphyry deposits of Andean belt and western US. Third, island arc setting where we have Kuroko sulphide deposits of Japan and porphyry CuMO skarn magnetite deposits. Number 4, hotspots, rifts and occlusions, failed rifts that is red bed copper, Kivin 1 type and copper. Fifth, cratonic areas, Witwatersrand, placer gold, Precambrian and Phanerozoic iron ores and Colorado type uranium evaporites and Bushveld types stratiform chromite, anorthosites containing FeTi and carbonatites which contain niobium, tantalum and rare earths. Finally, the idea of metallogenic province and their possible relations to global tectonics has become a potential tool for mineral exploration. The concept will narrow down the area of search for future deposits, thereby reducing the cost and time involved in our never-ending mineral exploration efforts. As was pointed in the subduction zone related CuMO porphyry deposits, there is a tangible zonation of different metallic ore deposits, Fe nearest to the trench followed by Cu, then lead, zinc, tin and lastly MO. This pattern would naturally help prospect for them in the right places in virgin though potential settings. Of course, there is a need for caution as geological ideas are never absolute like in mathematics. One thing is certain, however, recognition of metallogenic provinces and episodes serves a good guide for prospecting mineral deposits. The old saying that ore deposits occur where they occur need not be after all true. There are specific regions which we call metallogenic provinces and specific time which we call metallogenic epochs, which will guide us to look for the right thing in the right place.